To see a problem that comes up when you're not careful about communication cost, I want to talk about a real project in Stanford's data mining project course. The data being used was anonymized information about 1 million patients over 20 years, the medications they were given, and their medical conditions. The records were pre-processed to keep information about each drug in a separate record. That record contains the relevant medical history of each patient who took the drug. The average drug's record was about 1 megabyte long. So it doesn't look like a really big database, a few gigabytes of data. So what could go wrong? Well, again, the goal is to find drug interactions. So for example, you could calculate the fraction of people taking a drug A who subsequently got a heart attack, and the same for drug B. Then look at the intersection of the two sets of patients and see if they were significantly more likely to get a heart attack. So we need to look at each pair of drugs and do a statistical analysis of their two records. There are 4.5 million pairs of drugs in this study, so that's a lot of computation. But as we shall see, if we're not careful, the communication cost is so high that it makes it impossible to do the study using MapReduce. Okay, here's what, in a sense, is the obvious way to do the comparisons using MapReduce. We'll have a key for each pair of drugs, I and J. You can think of the set as a sorted list. It's the same thing, really. And the value will be the megabyte-long record for one of these two drugs. So what does the mapper do? Say, given drug I and its record, the mapper needs to generate 2,999 key-value pairs, one for each other drug J. The key-value pair for J has the key, that is, the set containing I and J. It's this. And the value is the record for I, which will represent that way. Notice that the mapper doesn't know the record for J, it only sees I and its record. And what does a reducer get? Say the reducer is the one for key ij. This reducer is going to get two key value pairs, one from the mapper for I and the other from the mapper for J. Formally, the input to the reducer is the key ij and the list of the two values associated with this key, the records I and J. We'll look at a baby example to see the idea. In this example, there are 3 drugs rather than 3,000. There will be 3 mappers, one for each of the 3 drugs. There are also 3 reducers, one for each of the pairs of drugs. It is a coincidence that the number of mappers and reducers is the same. In the real problem, there were 3,000 mappers and 4.5 million reducers. And for any number of drugs greater than 3, there will be more reducers than mappers. Okay, so the mapper for drug 1 produces a key-value pair where the key is the set 1, 2, and the value is the megabyte or so of data about the patients taking that drug. The mapper for drug 1 also produces another key-value pair. The value is the same, the record for drug 1, but the key is different. Here it is the set 1, 3. In general, the mapper for drug 1 will produce a much larger number of key-value pairs. The number of key-value pairs is 1 less than the number of drugs. Each key-value pair has a key that is the set containing 1 and one of the other drug numbers. The value is always the same, the record for drug 1. And the other 2 mappers do essentially the same thing, but with their drug number and with the record for that drug. Once these 6 key-value pairs are generated by the mappers, they are sent to the reducer for their key. And there they go. And once they arrive at the reducer, they are combined into a key and its list of values. For example, the input to the reducer for the set 1, 2 has the key 1, 2, and the list of values that were associated with that key and the various key-value pairs. Would be that. The total computation time is not insignificant. There were 4.5 million pairs, and each takes some work to process, even in main memory. Suppose 100 milliseconds of computation was required for each pair. That's about 120 hours of work shared among all the cores of all the compute nodes. Not insubstantial, but you can get it done in an hour by using 10, 16 core compute nodes. The problem is that there are 3,000 drugs. And the mapper for each drug created 2,999 key-value pairs, one for each of the other drugs. And for each key-value pair, a megabyte had to be communicated from mappers to reducers. You multiply that together and you get 9 terabytes, or 90 terabits. You try to squeeze that through a 1 gigabit Ethernet or anything with that speed, and it means 90,000 seconds, or about 30 hours of network use. And that's assuming there are no other jobs competing for the network. So let's see how we can reduce the communication cost without increasing the computation cost. The problem is that each megabyte long record gets replicated almost 3,000 times. If we don't replicate it at all, then everything has to be done by one reducer and therefore by one reduce task. That means no parallelism at all in the reduce part, and the wall clock time is too great even if the communication is really small. But there are compromises that can be made. We can group the drugs into several groups. The more groups we use, the more parallelism we can get, but the greater the communication cost. In a sense, the original attempt grouped drugs into 3,000 groups of size 1, which gives the maximum parallelism, but also the maximum communication cost. We'll focus on an example of 30 groups, each with 100 drugs. To be specific, the first 100 drugs will be in group 1, the next 100 are in group 2, and so on. I'll use the notation G of I to mean the number of the group to which the ith drug belongs. So here's the new map function. Now a key is a set of 2 groups rather than a set of 2 drugs. Keys actually look the same. They're a pair of numbers, such as looks like that. But now N and M are interpreted as numbers of groups rather than drugs. And of course, in this case, the range of the numbers is 1 to 30 rather than 1 to 3,000. Now, for each drug I, we produce 29 key-value pairs. And for each group number besides G of I, the group drug I belongs to, we have one key-value pair whose key consists of G of I and the other group number. And in all 29 key-value pairs, the value is the record associated with drug I, coupled with the number I itself. The reason we need to attach the drug number to its data is that, unlike in the earlier case, the reducer will not know what drug the records represent unless the drug itself is attached to it or embedded as a component of the record. Each reducer corresponds to a key consisting of 2 group numbers. The list associated with that key consists of 200 drug records, 100 for each of the 2 groups. The reducer for the pair of groups is responsible for comparing each pair of drugs that are one from each of the groups. There is a tricky matter of who compares drugs in the same group. 29 different reducers get all the drugs from group N, and we don't want them all to do it. A simple rule is to compare pairs of drugs in group N if M is 1 more than N in the end-around sense. That is, for N from 1 to 29, M is 1 more than N, and for N equals 30, M is 1. As a result, each pair of drugs is compared at exactly 1 reducer. The total computation cost doing the comparisons is thus the same as it was when the reducer was responsible for only 1 pair. There might be a small amount of overhead as the reduce function organizes the 200 records and moves its attention from one pair to another, but it is small compared to the real work of doing the statistical tests. In fact, since a good part of the statistics gathering involves only one of the 2 members of a pair, working in large groups actually saves some computation, but the computation time is not the big story. What changes is the communication cost. We still have 3,000 drugs, and each has a 1 megabyte record, but now the mappers make 29 copies of each of these records rather than 2,999, and that's a big difference. The actual communication cost goes down from 9 terabytes to 87 gigabytes, still substantial, but manageable on a student's computing budget.